Alright, well, welcome back. So in this section, we're actually going to be diving into a slightly different topic, and that is we're going to start looking at this idea of limits, but we're going to be taking these x values to be very, very large. That is, we're going to be studying these limits at infinity. To start this thing off, I'm just going to look at exploring this kind of nice little function, this rational function, x squared divided by x squared plus 1. Down below, I actually have kind of a nice little table of values as well as kind of a graph of this thing. First off, we're going to look at this table of values. In this case, what I want to think about is I want to think about taking these kind of values of x to become really, really big. In this case, I'm going to be looking at x's starting at 1 to 10 to 100 to 10,000, kind of just continuing to add on a 0. If you look at the outputs of this function, you can see that as my x's are becoming larger and larger and larger, it appears that these y values, or these outputs of this function, are appearing to start to stabilize. In this case, it looks like these outputs are getting really, really close to 1. In this way, what I have is I have my x's are going to become really big. I'm going to view this as my x's are tending to infinity, and at this stage, my functions are getting really, really close, into this case, a 1. What I'm going to write down for this is going to be a limit as x approaches infinity of my function f of x, which in this case is an x squared divided by x squared plus 1. I'm going to say that this function, as x goes to infinity, this function is tending to 1. The kind of way out in the outskirts, this function is going to look a lot like this function 1. Likewise, you can do the exact same thing, but off into the other direction. You can see that as my x values become very, very large negative numbers, going from -1 to -10 to -100, so on down that list, you can see that as my x's are going towards negative infinity, it appears that my function outputs are also going to be, in this case, tending to 1. In this case, I'm going to say that the limit as x approaches negative infinity, so as my x values become very, very large negative numbers, of my function x squared over x squared plus 1, this limit is also equal to 1. And you can see this if you look over here on the graph. If you kind of go out for really large values of x, it appears that the y values are kind of stabilizing. It's flattening out in this case. The same exact thing is happening over here as well. As I go off to the left, it appears that my y values are stabilizing. And in this case, they're actually both going to the same value. They're both going up to this value of 1. And I'm going to denote this with one of these classic little horizontal asymptotes. I'm going to say that this function actually has a horizontal asymptote at y equals 1. Okay, so the next thing is actually just the definition that I kind of just highlighted. It's this idea that if you have some function defined on some interval that's going off to infinity, then I'm going to use this notation that says the limit as x approaches infinity of this function f of x is going to equal this value of L. That means that these y values can be made arbitrarily close to this value L. There's a couple different situations that actually can come up in this case. The first is kind of the one that we just saw. It's this idea that you kind of have this nice swooping curve and it gets really close to this line L. You can also have a bunch of crazy oscillation as well. This function over here is going to be doing the same thing, even though it's kind of bouncing up and down above and below this horizontal asymptote. It's kind of, there's some oscillation and then it appears to kind of stabilize. It does flatten out at some point in time. And then the last picture is that same idea, but not nearly as extreme in this case. But in all of these situations, I'm going to have this idea that my function is going to be tending to some value. This idea that my function f of x is getting really close to this value of L as my x's are becoming very large. So sometimes people use this kind of alternative notation for this idea of limits, this kind of formal structure, this limit as x approaches infinity of this function f of x. You can also do this with some of these little arrows as well. You can say that this function f of x is going to get really close to L, and then when is it doing that? It's doing it as x approaches infinity. We've actually seen a couple of these kind of ideas of horizontal asymptotes before. You've kind of maybe touched on them a little bit in a trig class or in a college algebra or algebra 2. The kind of go-to example for this is going to be the arctangent function. And what I have over on the left is going to be this table of values for the arctangent. I also have the graph of this thing. It's this big kind of crazy looking S shape. But the interesting thing about the arctangent function is that it actually has two horizontal asymptotes. You can see that off to the right, as my x's become very large positive numbers, it appears that my limit's going off to a positive pi over 2. Whereas if I take very large negative numbers, my limit in this case is going off to a negative pi over 2. So there is a little bit of difference going on in this case. I have a horizontal asymptote of pi over 2, and I have a horizontal asymptote of negative pi over 2. And that's coming from these two different kind of limiting values. This case that my limit as x approaches infinity, this positive infinity, that's kicking out this positive pi over 2. Whereas the limit as x approaches negative infinity is going to be kicking out this angle value of negative pi over 2. So that's kind of a nice example in that we have two of these horizontal asymptotes, which is something that's a little bit different than what you might have seen in a college algebra course. A lot of those ones you end up having just one horizontal asymptote, but there's no reason why I couldn't possibly have two. Alright, so to wrap this kind of intro section up, I'm just going to look at a couple other really classic looking functions. In this case, I'm going to be studying this kind of reciprocal function f of x, which is 1 over x, and I'm also going to be looking at this function g of x, which is just simply the function x. In this case, I've also made this giant table of values to kind of see what's happening. This first one, you can see I'm going to be taking these input values, these x values, as they're becoming very, very large. You can see that as these x's become huge, this idea of 1 over x is going to kick out a very, very small number. And if you think about it, that makes sense. I'm going to take 1 and I'm going to divide it into a ton of pieces. Each of those little pieces are going to be very tiny. You think about having 1 1,000th or 1 10,000th or 1 1,000,000th. These are very, very tiny numbers. So in this case, you can see that my limit as x approaches positive infinity of 1 over x, this limit's actually going to kick out a 0. You can also see from the negative side, as x's go down to negative infinity, my outputs are also going to be kicking out a 0. I'm going to have this idea that the limit as x approaches negative infinity of this function 1 over x is also going to be a 0. If you look up here, I can actually have the graph. This function f is going to be this y equals 1 over x. You can see that this thing actually does in fact have this kind of classic horizontal asymptote existing. I have a horizontal asymptote at y equals 0. This thing kind of flattens out way out in the outskirts. It flattens out there as well. The other one, just to kind of see some things that don't have asymptotes, is your classic linear function g of x, which is just equal to x. Obviously, if you take these values for your inputs, they're going to be the exact same things for your outputs. So what ends up happening in this case is you have a limit as x approaches infinity. Well, if your function is just x, that thing's going to explode. It's going to become arbitrarily large. So this limit is actually going to kick out a positive infinity. Similarly, if you start looking at this in the other direction, if you take a limit as x approaches negative infinity of this function x, well, as my x's become very large negative numbers, my outputs are going to become very large negative numbers. So it again is exploding. It's going to this giant number, and in this case, this giant number is going to be a negative infinity. It's kind of continuing to get larger and larger, but it's still keeping on this negative sign as well. I'm just going to kind of wrap all of this up into one little fact. It's a fact that we'll use a few times throughout this section. It's kind of this classic looking at these limits of these kind of reciprocal looking functions or these kind of monomials, these single little terms you see in polynomials. In this case, I'm assuming my r value is just going to be some rational number. Just kind of think of your favorite fractions. You're going to have limits of the following form of kind of 1 divided by x to the r. All of those limits are always going to be kicking out these values of 0. The idea is that if you think about 1 divided by an enormous number, my x's in this case are becoming huge. So I'm going to have something like 1 divided by this huge number, and that's often going to kick out this idea of 0. Likewise, if I take some number and I raise it to a power, well, that raising it to a power is not going to kind of kill off this fact that my inputs are becoming massive. I'm taking some enormous number and I'm raising it to some power. In that situation, I'm still going to be kicking out this kind of huge number again. So what's happening is that my limit as x is going to blow up, that expression is also going to blow up. So I'll have this limit as x approaches infinity of x to the r is going to equal this kind of positive infinity. For the other direction, we have to be a little bit more careful, I guess. We're going to be taking limits as we go off towards negative infinity. In this case, I want to start thinking a little bit about making sure I can actually take x to the r. This idea that if I'm working with square roots or something like that, my functions aren't actually even defined over kind of way to the left. But if I do have kind of an x to the r that is defined, So you think about something like x to the 3 halves. That actually does work. Well, in that case, if you can do it, if you still are in this structure of 1 divided by x to the r, well then I'm still going to take 1 divided by some huge number. It might be a huge negative number, but it doesn't really matter. What's going to happen is that in limit, it's still going to kick out this 0. It's this idea that you take a number divided by a massive number, it's going to kick out a 0. So that's kind of the really quick intro on this section. What we're going to do is next kind of dive into a few kind of nitpicky little examples to start seeing kind of what's actually happening in this world.